Hey everyone, welcome back. Today, we're going to dive into a really fun computer science puzzle. We're going to take a binary tree, one filled with just ones and zeros, and figure out a super elegant way to sum up every single path from the top to the bottom.
So, just picture it. You have this tree, and every path from the very top root down to a leaf at the bottom spells out a binary number. The big question is, how do you actually take all of those paths, turn them into numbers, and add them all up into one final sum? All right, so before we jump into any code or fancy algorithms, let's just make sure we're all on the same page about what the goal is here. Let's nail down exactly what a path in this puzzle even means. First things first, a root-to-leaf path. I mean, it's pretty much what it sounds like, right? You start at the tippy top of the tree, that's the root, and you just follow a path all the way down until you can't go any farther, until you hit what's called a leaf node, which is just a node with no kids. Okay, so here's where it gets cool. Each of these paths isn't just a sequence of nodes, it's a binary number. So for example, if we take a path that goes through a 1, then a 0, then another 1, we get the binary string 101. And if you remember your binary, 101 is just the number 5 in our normal, everyday decimal system. Our mission is to do this for every single path from the root to a leaf, and then just add up all those numbers.
So you could do that. You could traverse the tree, build up all these strings like 101, put them in a list, and then convert each one to a number and add them up. But that feels a little clunky, doesn't it? There's actually a much more elegant, kind of clever way to do this.
So check this out. This is the big idea. Instead of messing around with strings, we can build the number mathematically as we go down the tree. Just think about what happens when you add a new digit to a binary number. When you add a bit to the end, you're really just shifting all the previous bits to the left. And shifting a binary number left is the exact same thing as multiplying it by 2. So as we go down the tree, we just take our current number, multiply it by 2, and add the new node's value. It's a beautifully simple way to get to the same answer.
And for all you programmers out there, there's an even cooler, faster way to write this. Instead of multiplying by 2, you can use a bitwise left shift operator. It's doing the same exact thing mathematically, but it's often a single, lightning-fast instruction for the computer. It's one of those neat little tricks that makes your code just fly.
Okay, theory is great, but let's actually see this thing in action. We're going to walk through an example tree step by step using a depth-first search. That just means we're going to go as deep as we can down one branch before we backtrack and try another one.
All right, here we go. Let's take the first path all the way down the left side. We start at the root, which is a 1, so our current number is 1. We then move left to a 0. Using our formula, the new number is 1 times 2 plus 0, which is 2. We go left one last time to another 0. Now our number is 2 times 2 plus 0, which gets us 4.
And boom! We've hit a leaf. So, our first number is 4. We'll just hang on to that and add it to our running total. Okay, so what happens now? The algorithm is smart. It backtracks. It goes back up to that node where our number was 2, but this time we're going to explore its right branch, which has a 1. So our new calculation is 2 times 2 plus 1.
And that gives us 5. That's our second leaf, so we add that to our total. We had 4, so now we're at 9.
All right, one last path to go. The algorithm backs all the way up to the root and is now ready to explore the entire right side of the tree. We start again with 1. The first step down the right side gives us 1 times 2 plus 1, so now we're at 3. Then we take one final step down, giving us 3 times 2 plus 1.
And that gets us to 7. We take that 7, add it to our running total of 9, and we're done. So let's recap everything. We found 3 paths. They gave us the numbers 4, 5, and 7. You add those all up, and what do you get? 16. That's our final answer.
So we got the answer, 16. Great, but honestly, the number itself isn't the most interesting part. The real takeaway here is understanding why this method, building the number on the fly, is just so much better. I mean, look at the benefits. This whole thing is just elegant. We solve the entire problem in one single pass through the tree. That makes it super time efficient. And memory? We're not storing a bunch of clunky strings. All we have to keep track of is the current number as we go down. There's no extra baggage, no costly conversions. It's clean, it's fast, and it's smart.
And that really brings us to a bigger, more powerful idea. This pattern of building a solution as you traverse a data structure, instead of collecting a bunch of stuff and processing it all at the end, is incredibly useful. So I'll leave you with this question to think about.
what other problems can be solved by building the answer on the fly. It's a really powerful pattern to have in your toolbox. Thanks for joining me.